We spent some time yesterday looking at an experiment called Young's double slit experiment. And in that experiment, Thomas Young shone light, monochromatic light, one color light, through two openings. That light diffracted and formed an interference pattern as a result of these two diffracted waves encountering each other. Because light needs to have something to reflect off of in order to see it, we can't just stand above this apparatus and see these lines of constructive and destructive interference. Rather, we have to put a screen at the other side of it, the other end of it, in order to see these areas of constructive and destructive interference. What we end up seeing as a result of shining, say, red light through these two openings, diffracting and interfering, is a bright spot right here in the middle. We call that our central bright spot, our central antinode, our central maximum, our central area of constructive interference. And we usually assign a number of 0 to that to that central bright spot. And then next to that, we actually have an area where there's no light. We have destructive interference. The light completely cancels out. Crest meets trough, and we see nothing there. But beside that, we see another area of constructive interference, another bright spot. We're going to assign a number of 1 to that. And then another one, another dark spot, and then another bright spot that we'll assign a number of 2. And then a dark spot, and another bright spot, and so on, and so on, and so on. On the other side, it's symmetrical, looks the same. First order antinode, first order bright spot, first order maximum, so on, second order, third order, and so on. We learned 2 equations that will allow us to analyze what we see up here right now. The first equation is the one that we can always use, or at least that we're always allowed to use, because it's not an approximation. D sine theta over n, is that right? D sine theta over n. Let's identify some of the variables in here. Lambda, of course, is the wavelength of the light that's going through these 2 openings. Red light, 10 to the minus 7 meters, something times 10 to the minus 7 meters. D is the distance that separates these 2 openings. Now, sometimes you're not given a value of D, the distance between the openings. Rather, sometimes you're given a value of something that says maybe like 1,000 lines per centimeter. That's not D, rather that would be 1 over D. So you're either given the distance between the openings as D, converted to meters, or you've got what we call a diffraction grating, which has multiple openings, not just 2, but maybe 100 or maybe 1,000 openings, and we have to find D from that. All you're going to do, by the way, if you're given 1 over D, is flip it over. Right? 1,000 lines per centimeter would be the equivalent of a D, a small d, of 0.001, 1 over 1,000. So there's D. If you got it, great. If you don't, because you have this, then get it, and then keep going. Theta stands for the angle between the central maximum and the third order maximum, or between the central maximum and the first order minimum, or between the central maximum and the 14th order minimum. It doesn't really matter, as long as n is consistent with that. Now, in this case, we measure theta there, and then we determine n to be 3. 3 minus 0 is 3. In this case, we measure theta again, and then we determine n to be 0.5. Because the first order maximum is 1, the first order minimum would be 0.5. 0.5 minus 0 is 0.5. We plug in our numbers, and we solve for lambda. But what if we don't have the value of theta? What if we've got a value of, let's say, x? What if we've got a value of x that maybe is the distance from the third order maximum to the central maximum, or maybe it's from the third order maximum to the second order minimum? Well, we do the same thing there as we did with theta. We make sure that n agrees with it, n is consistent with it. In this case, we'd say n is equal to 3. 3 minus 0 is 3. In this case, we'd say n is equal to 1.5. 3 minus 1.5 gives me 1.5. Again, it all works out as long as you make sure that x and n are consistent with each other. It works out if Do you remember the big if for this equation? That first equation is always valid. The second equation is valid if theta is greater than 10 degrees. If you're given the angle already, says it's 8 degrees, then go ahead and use that equation if it looks like it's convenient for you. If you're not given the angle and you want to determine whether that equation is valid for you or not, then we have a little shortcut, a rule of thumb that will help us to determine whether we can use that equation or not. Do you remember what it is? Sorry, say it again. Oh, sorry. Yeah, you're right. Yeah. Having trouble with my little alligator, right? If theta is less than 10 degrees, you're absolutely right. Yeah, theta is less than 10 degrees. But how do we determine if theta is less than 10 degrees by a rule of thumb as opposed to actually calculating theta each and every time? What we're going to do is compare. We're going to compare L, which is this distance right here, with x, with 10 times the value of x. So what we're going to do is calculate the value of 10 times x. X is 0.1 meters, then multiply it by 10. Compare it with the value of L. If L is greater than 10 times x, okay, then that's a good rule of thumb to tell you you're allowed to use this equation. I'll tell you what, 90% of the time, 95% of the time, you're going to find that the angle is less than 10 degrees. You're either going to be told that it's less than 10 degrees, or you're going to find L, you're going to find 10 times x, and you're going to find by that your angle is small enough that you're allowed to use that equation. Every once in a while, you're not going to be able to use this equation. So then you've got to go back and use this equation. But we need theta in order to do that. Well, if you've got the value of L and you've got the value of x, let's say from the central maximum to the third order maximum, then all you're going to do is a little bit of trigonometry in order to find the value of theta. We'd say in that case tan theta is equal to opposite over adjacent. Solve for theta, and then once you solve for theta, use that equation. Now, you can solve for theta every single time. Every single time it's measured from the central maximum, you can solve for theta, determine if the angle is less than 10 degrees or greater than 10 degrees. You don't need to use this rule of thumb right here, but that rule of thumb right there is quicker, right? It's quicker and it's shorter. So if we use that rule of thumb and we find that, okay, we can't use this, then we got to find the angle. But if we use the rule of thumb and it says that L is greater than 10 times x, it saves us the bother of finding the angle. Make sense? Here's my take on it. If we have to find the angle every time to see if it's below 10 degrees, then why wouldn't we just use this equation? And if we got to find the angle anyways, it doesn't even really matter if this equation is valid, because we have the angle, we're able to use this equation. All right? All right. What if, let's say I shine red light through the openings. I get an interference pattern that looks like this, right? Here's a bright spot, here's another bright spot, here's another bright spot, here's another bright spot, right? We have these areas of constructive and destructive interference. And of course, on the other side, we have the same thing. First order maximum, second order maximum, third order maximum, and it keeps going. How far does it keep going? Well, it depends upon circumstances, but it keeps going for a while anyways. What if I shine a different color through there though? What if I shine still one color, but it's not red anymore? Maybe it's blue or violet this time. Well, if you remember when we had a prism and we shone light through a prism, white light through a prism, or let's say we just shone two colors through the prism together, we found that red light bent the least and violet light or blue light bent the most. Blue light, violet light refracts more than red. Blue light, violet light bends more than red. Make sense? If we're talking about diffraction, we would find that blue light or violet light would bend less than red. So it would look something like this, with this being our central maximum, this being our first order maximum, second order maximum, third order maximum, 1, 2, 3. So blue light bent more than red right here with refraction. Blue light diffracts or spreads out less than red through a diffraction experiment, whether it's a diffraction grating or a double slit experiment. Make sense? Is that okay? What if we use both colors at the same time? What if, just like in this prism, we shone white light through there consisting of 2 or 3 or 4 or 5 different colors? Then the pattern that we're going to see is going to look something like this. If I shine blue and red through at the same time, then this is the pattern that I end up getting, right? It's as if the blue and the red were separate from one another, except that they're not separate from one another. This time, it's the red and the blue that are diffracting different amounts. Remember, the red diffracts more than the blue, whereas the red refracted less than the blue. We end up getting, basically, if we have all the colors there of white light, we end up getting a rainbow for each maximum. Now, what I want you to understand when you see this is that this isn't a first order maximum and this a second. These are both our first order maximum. The first order max for blue and the first order max for red. Does that make sense? So what if you get a problem where you have more than one color like this? If we saw the red one right here, we could do that, right? We've done problems like that. If we saw the blue one, we could do that. But if we see this, which is the red and the blue together, that becomes confusing for us. But it doesn't need to. If we're given data for the red, then pretend the blue doesn't exist. It's there. Look, it's there, but we're pretending that it's separate. So really it looks like this, but if we want to analyze these together, we pick a color like red if we have data about the red, and analyze just the red, pretending the blue's not there. Or if we have data about the blue, then let's pretend the red isn't there, even if they both do go together, even if there's 4 colors in between the blue and the red. Pick a color for which you have data and ignore the rest. So don't look at this and say, all right, this is my central maximum, first order maximum, second order maximum, third, fourth, fifth, sixth. Look at this and say, this is my central maximum. Okay, this is my first order maximum for all the colors, second order maximum for all the colors. Pick a color for which you have data about, and then pretend the others don't exist. Basically, turn this problem into either this problem or this problem. Does that make sense? Don't make it harder than it has to be. All right? Now, we had some questions for homework, 3 sets of them, although you did work on some of them in class, so I suspect we're not going to need to go over some of those questions. 3 sets of homework that we had due for today were on page 689, 691, and 693. Are there any issues with any of those questions that we saw on either of those, or on any of those 3 sets of questions, those 3 pages? 689, 691, and 693. Yep. Okay. Anybody else? Yep. Number 2 on the 3rd set. It seems, you know what, I want to go over number 1 as well, because it seems to me the answer for number 1 in the book was wrong. Anybody find the answer was wrong there? Okay, we're going to do number 1 anyways, even if you guys didn't find that the answer was wrong. We'll do number 1, and then we'll definitely do number 2 as well. All right, number 1 says, an unknown wavelength of light is incident on a diffraction grating with 2,500 lines per centimeter. Probably want to draw attention to that and make sure that I recognize that it's not D, but rather that's 1 over D. Lines per centimeter, lines per millimeter, lines per meter is going to be 1 over D. The distance between the central antinode and the third dark node is 20 centimeters. The central antinode, the first antinode, the second antinode, the third antinode. The distance between the central antinode and the third dark node is 20 centimeters. That's x, and n is going to be 2.5 there, because we're going to, you say the third order node, or you could say the 2.5 order antinode, if you want to think of it that way. We know that L is 50 centimeters, and we know what 1 over D is, right? 2,500 lines per centimeter. Look, we see this data. We want to use the equation lambda is equal to xd over n times L, but we want to check to make sure that we're allowed to use it. Okay, we can calculate the angle. Right? We know what L is, we know what X is. We can find the angle right there and see if it's below 10 degrees. Or we can just use our little rule of thumb, which says, is L greater than 10 times X? Is it? Well, the value of L is 50 centimeters. The value of 10 times X is 200 centimeters. Is L greater than 10 times X? No. We can't use that equation. Like L isn't even close to 10 times X. So we're definitely not allowed to use that equation. So what do we got to do? Now we have to find the angle. We don't have a choice. Okay, we know what L is. It's 50 centimeters. We know what X is. It's 20 centimeters. Okay, let's find the value of theta. Anybody catch that, by the way? Anybody do the little test and find that we couldn't use that equation? All right, let's say tan theta is equal to 20 over 50. Theta ends up being equal to, I think it was something like 21 point something degrees. 21.8 degrees. Thank you. Now that we have that angle, we don't even need to use this equation, right? We wanted to use it right off the top, but once we get the angle, we might as well just go back to the one that always works for us. D sine theta over n. So D is, we got to find that. 1 over D was 2,500. D would be 1 over 2,500. What's that work out to be? Which gives us 4 times 10 to the negative 4 centimeters, which gives us 4 times 10 to the minus 6 meters, right? Because we want to convert it to meters, but only after we've found the value of D. So let's plug that in. We have D is 4 times 10 to the minus 6. Sine theta is sine 21.8 degrees over the value of n, which we said was 2.5. And I think when we do that, we do not get the answer that's in our book. I think we get a number that's quite significantly different, actually, than the answer that's in our book. Let's try it. Let's figure it out here. Make sure you're in degree mode. And let's calculate it here now. We say 4 times 10 to the minus 6 times sine 21.8. And let's divide that by 2.5. We get 5.94 times 10 to the minus 7. Anybody get that value? What's the value they gave us in the book? 6 point something, I think, wasn't it? 6.4 times 10 to the minus 7. That's quite a difference, eh? Like 5.9, 6.4 times 10 to the minus 7. If you're dealing with an angle that's less than 10 degrees, there may still be a small difference. Your test or your diploma exam will be keyed to accept both of those if the angle is below 10 degrees. But if you got a big angle like this, 21.8 degrees, it's only keyed to accept this one, not the 6.4. Okay, 6.4 would definitely be marked wrong. Okay, you have to know that when it's above 10 degrees, you can't use that other equation. Yep. Yep. Christian? We always want to be in consistent units through these problems, and since we're using but you know what, I didn't actually end up using L. Well, sorry, I did use L and X, I guess. I did it when I was finding the angle. I didn't change it there because in the end the ratio of opposite to adjacent, it doesn't matter whether we're doing centimeters or meters there, right? It doesn't make any difference. I could have left D in centimeters there, but if I had of, then I would have got an angle, a number for lambda, which was in centimeters. And I typically don't want lambda to be in centimeters. So my suggestion is just always convert to meters there, except when you're dealing with lenses and mirrors. And even then you can still. Okay. But if in doubt, go meters here. we would have gotten, by the way, what, 5.94 times 10 to the minus 5 centimeters, which would have been okay. But odds are, if it's a multiple choice question, it's not going to be one of the options, right? It's going to give it to you in meters or nanometers. Does that make sense, everyone? Right? If you got to do your little check. Okay, you got to do your check. And 9 times out of 10, the check is going to pass, and you're going to be allowed to use the equation you want to use, whichever one that is. But 1 time out of 10, you have a situation like this where it doesn't pass. So you got to find the angle, and then from that you got to do your thing with the equation that always works there. Yep. All right, let's take a look at number 2. 2 says, how many lines per centimeter are there in a diffraction grating if the third dark fringe is 5 centimeters from the central antinode? So once again, here's my central antinode, first bright fringe, second bright fringe, third bright fringe. This would be my third dark fringe. We're going to say n is equal to 2.5 again. We're going to say x is equal to 5 centimeters. Right, the distance from the central antinode to the third order dark fringe. We're going to say that L is 60 centimeters, and we're going to say that lambda is 500 nanometers. Now we want to find 1 over d, right? But I'm going to put a little star by that, because remember that in order to get that, we're going to find d, and then we're just going to flip it over. All right, looks like given what we have here, we want to use lambda is equal to xd over n times L. So let's do our little check. Is L greater than 10 times x? Well, 10 times x is 50 centimeters. L is 60. Is L greater than 10 times x? Yeah, it is. We're allowed to use that. Barely, but barely works. Do the check. 9 times out of 10, it's all going to be good. 1 time out of 10, it's going to work out like question 1 did, and you can't use that equation. All right, we're solving for d, or at least we're kind of solving for d here. Lambda times n times L over x. Lambda is 500 times 10 to the minus 9 meters, times n, which is 2.5, times L, which is 0.6. Christian, you see what I'm doing there? I want to be in meters. Even though technically it could go centimeters, you got to be consistent, so there's going to be some unit conversions to do somewhere. You might as well just go all meters. X is 5 centimeters, or we're going to make it 0.05 meters. Let's calculate that value. I get 5 times 10 to the minus 9 times 2.5 times 0.6. And we're going to divide that by 0.05. It gives us a D of 1.5 times 10 to the minus 7. That's meters, right? Okay, you want to find lines per centimeter. Convert that to centimeters now. That's going to be 1.5 times 10 to the minus 5 centimeters. And then, what are you going to do? Now comes the easy part. This is centimeters. We want 1 over centimeters, so let's flip it over. Let's take that number that we have. This is meters, remember. Divide it by 100 to get centimeters. Or sorry, multiply by 100 to get centimeters. Doesn't like multiply and divide at the same time, I guess. 1.5 times 10 to the minus 5, and then literally we just flip it over. 1 over that gives us 6.67 times 10 to the 4. Lines per centimeter. Is that the answer they had in the book? Sorry, a little bit of a typo there, a little bit of a mistake, right? This I had typed in wrong. I typed it in as 5 times 10 to the minus 9, not 500 times 10 to the minus 9. That gives us 1.5 times 10 to the minus 5 in meters, 1.5 times 10 to the minus 3 in centimeters, which gives us 6.67 times 10 to the 2 in lines per centimeter, which is what the book had, right? So those of you who agreed with me when you did that probably did the same thing as me. and typed in 5 times 10 to the minus 9 instead of 500 times 10 to the minus 9. All right, we're good there? Any other questions, sir?